Here is the question that I ended the previous part of this lecture with, and the calculation is fairly simple. You use the work equation, and we can see that the sum of x components of these two forces will be a 3 Newton force to the right, and so when we now multiply that by the displacement, we come up with 6 joules. Or you could think of it as the 5 Newton force doing 10 joules of work, and the 2 Newton force doing -4 joules, and that again gets you 6 joules. Now that we sort of know the structure of this theory, I'm going to once again compare impulse with work. And so we start with two conservation laws, conservation of momentum and conservation of energy. And we're writing them saying that the change of momentum is the impulse, or the change in energy is the work done by external forces. And so at this stage, the theories look very similar. And now it splits into cases. Either we are in an isolated or not isolated system, or a closed or not closed system. And in the isolated or closed cases, the impulse or the work just end up being 0. And in the not isolated or not closed cases, we end up with equations for how to calculate impulse and work, which look extremely similar to each other. And so overall, you can see that these theories are very, very similar in their structure. Real systems are usually not single particles, so how do we deal with them? Well, at least objects which are reasonably rigid can be approximated as particles, and so in our cart and spring system, we could think of the carts as particles. What about the springs, though, and what about the wheels which are rotating internally to the system? Well, as long as they're light, we can treat them as massless. However, they're still going to have internal energy, and that's going to be captured in the fact that we think of these particles now as interacting. There's internal energy in the system. So non-rigid objects can be treated as systems of interacting particles. Let's try and reformulate our theory to apply to systems of interacting particles instead of just to a single particle. The first barrier is that our equation of motion that we've been using doesn't work for a system of particles because we don't have one thing of inertia m moving with an acceleration of a. We have a whole bunch of different things moving with different accelerations. But we do know from an earlier unit that we can write an equation of motion for the center of mass, which looks like this. So now with that version of the equation of motion, and again uniformly accelerated motion, and a definition of the change in the kinetic energy of the center of mass, this looks good, because this looks just like our starting point for the work done on a single particle, except we've got a bunch of cm's in subscripts all over the place. So we should be able to go through exactly the same procedure, blah, 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 and come up with an expression for the change in the kinetic energy of the center of mass that looks like this, which will be valid for constant forces in one dimension acting on a system of particles. But now we've actually hit a bit of a hitch. Sure, we've got an expression for the change in the kinetic energy of the center of mass, and that might be useful, but what we were actually after was the work. And the work is the change in the total energy. All we've got is one piece of the change in the kinetic energy. We don't even have the change in the convertible kinetic energy included in there. And so this change in the kinetic energy of the center of mass is not the work. The real problem here is that I've got a whole bunch of different forces and they all have different force displacements. If I compare the force displacement of what I'm calling external force 1 with the force displacement of what I'm calling the external force 3, it's not obvious on the diagram that they're different, but if I copy them out by themselves, you can clearly see that they're different. And the problem here, of course, is that the spring is compressing, and so because of that, the relative positions of the objects in the system are changing. But what we can do is go agent by agent. The work that agent 1 does on the system has to be the negative of the work that the system does on agent 1. That's conservation of energy. Any energy that agent 1 gives to the system must have taken from agent 1. And so I can write the work by the system on 1 as a product of the force that the system exerts on 1 times the force displacement. And that force by the system on 1 by Newton's third law is just the negative of the thing I'm calling external force 1. And so, since that is now overall the negative of what I'm looking for, right, that's the work by the system on 1, and I want the work by 1 on the system, I can just cancel the negatives. And so I have this work 1, which is just the external force 1 times the force displacement that goes with it, and so on for works 2, 3, and so on. And so I can write the work done on the system as a sum of works by different external forces, and I can write it compactly this way, which is a more general work equation. It's not fully general yet because it still only applies to constant forces. Let's check your understanding of how to calculate works this way. So here we have two carts connected together by a spring, and they're moving to the right, and there's a 5 Newton force acting on one to the right and a 2 Newton force to the left on the other. Cart A moves 5 meters, but because the spring compresses during the motion, cart B doesn't move quite as far. It only moves 4 meters. And we're considering the system to be the 2 carts and the spring. And so let's find the total work done on this system.